Practice a rural substation. I mean, I know most of them personally.
So it's more or less about 10,000 to 20,000 customers per small.
In this case, but this may change.
So if we gather information on each substation and we cluster that information, we can say instead that I have 10,000 meter rigs, I have 5 meter rigs. All 5 of them are this type of load. All the others are this type.
Yeah. What you are suggesting, what I'm going to suggest right now, is hierarchical processing of this information. There are several layers of processing. Please. Good question. This is what I mean. It depends. So far, we have been living over 100 years without this information. I mean, we have been, but in the 60s and 70s, owing to major blackouts, they decided to deploy energy management system as transmission system, and they decided to capture remote terminal units every 4 seconds, every 10 seconds, for all substations, transmission substations. Now it seems that distribution substations are becoming like transmission substations in the sense that they are active. They are including, embedding distributed generation, electric vehicle, energy storage, whatever. So the distributed generation, for instance, must be closely monitored because there can be, I don't know, suddenly a ramp, wind ramp, or maybe suddenly sun made a cloud or whatever, and there could be a very low voltage, and the sun rises again, and then there is a high voltage. So if we pretend to track and to monitor as closely as possible distribution substation, we need, if we want to estimate the state of each electrical bus, the only thing to do that is to include smart meters. Even if we include smart meters, the redundancy will be barely 1. And in transmission system, we have 4. Even if we add these smart meters, this will be basically like allow flow. I mean, the estimation will be, for this reason, I'm also suggesting that we should add distribution automation, because distribution automation may allow you to add intermediate measurement at the intermediate points. Typically, where there is a switching operation, it's in the middle of the feeder, 1/4 of the feeder, 3/4 of the feeder, there are switching points to change the topology. So in those points, we may have additional information to add redundancy, because otherwise there will be no redundancy at all. There will be a low flow. So smart meters are necessary to achieve observability of the distribution system, or equivalent measurement devices. Sorry. And also personal injuries, personal damages. So there will be. So the question is how frequently. This is not a clear answer. I mean, every minute, maybe in my opinion, every 10-15 minutes might suffice, because usually transmission system, distribution system, the time constant of evolution of loads, aggregated loads, is relatively low. So maybe every minute is enough, not every 5 seconds like the synchrophasor. For that reason, I don't think synchrophasor may be necessary at this level, at the distribution level. But anyway.
On this part of the system, medium voltage radial, the single phase estimator is valid, or we have to start taking into account
it depends on the region. In Europe, according to my experience, single phase state estimation is enough for medium voltage. In the USA, it's not. In the USA, even medium voltage system is unbalanced. However, in low voltage network, you must resort to unbalanced state estimation, to 3-phase state estimation or single phase estimation, which are coupled with the cause of magnetic coupling.
Do we need to do 3-phase estimation with low voltage?
Because because most customers are single phase. Yeah.
A lot of countries now are switching to 3-phase customers, or they're having mesh networks.
Yeah, actually, I'm a 3-phase customer myself, so many years ago.
Can we expect distribution level
Yeah, maybe. They are so cheap, you know. We have PMUs here in my cellular, so I mean, GPS signal. So GPA is so cheap now that why not? I don't know. I mean, but it could be useful for, I don't know, synchronizing this photovoltaic voltage with, I don't know. Might be useful, but it's not as imperative as in transmission system, probably.
I'm just going to ask you a question about GPS. Because obviously, to some extent, GPS is provided for us by the US military.
Mm-hmm.
So maybe at some point we could.
Galileo. We have to resort to Galileo. Yeah, you are right.
So,
Yeah.
would that have a, would that really, if the GPS involves was switched off, would that have a major impact on?
Yeah, you are right. And I would add something to that observation. GPS, I mean, PMUs are not the panacea many people try to sell. I mean, PMUs, as I said, is simply a way of synchronizing waveform from different places. But they are not more or less accurate than conventional measurement. It depends on the instrumentation transformers. If they are using the same instrumentation transformer as conventional measurement devices, they have the same accuracy. So sometimes some people are selling that PMUs are so accurate that we can get rid of the state estimation. This is false. It's not true. What happened if the substation suddenly lost the communication channel? So you will always have to use processing PMUs. And PMUs are not the Bible. I mean, it's fashionable, like big data. But big data is another name for statistics. Right? That's all. They are trying to sell. Statisticians are boring, and they need a revival. They need a revival. So they have invented big data because of Google algorithm for searching information, this kind of thing. It's true. You have to have efficient algorithms for handling huge amounts of databases. Okay, and processing and extracting valuable information for those databases. But this has been always around in the statistic world. There is no new statistic theory. Just new empirical algorithms, artificial intelligence or whatever. Another keyword, artificial intelligence in the 90s. That fortunately for us is slowed down. Okay. I'm enjoying today. Because you are participating, which is what I like. Okay. I will not finish my presentation, but I don't mind. I can continue in the afternoon if you want. Okay, so hierarchical estimation. Well, we have a basically encapsulated estimator. This estimator that basically didn't relate with the networks. The estimator was connected with the subtransmission and distribution and was also connected in Europe and USA to other TSOs, to other areas. But the interaction was almost null. I mean, actually the estimator so far is a tool which is encapsulated, replaces subtransmission system by equivalent injections. This is a subtransmission and distribution system, just equivalent injections, and replaces the external system by a crude external equivalent, basically the tie lines. So the estimation of the tie line, for instance, is not very accurate because there are radial basically, and the estimation may not be good enough. So the estimation so far is a non-interacting application with neighbors. It's isolated, encapsulated application. And this is no longer possible. As you have seen, there are many new information. This is what summary of what I have explained so far. I don't repeat. So the idea is, my point is, sending everything in real time to a single central energy management system is no longer technically feasible, or at least economically feasible. For that reason, I think we should resort to a hierarchy of estimation or energy management system, which is the substation level energy management system based on a local state estimation, processing the substation information, the conventional transmission system operator estimation, and most likely a central place, a regional state estimator coordinating the tie lines and the interconnection between areas, basically. In other words, try to process as much raw information as possible at the substation level. This is my point. And I've been selling this idea for the last 10 years unsuccessfully so far. And then TSO estimator, where it will receive probably a small percentage of information that cannot be locally processed because there are no computing power or whatever, or the substation is not locally observable. Okay, advantages. Okay, we can process a lot of raw measurement locally. We don't need to aggregate raw measurement. I showed you in the topology processing that some measurements are lost when you obtain the batch branch model. So this way, you don't need to aggregate, or you don't need to discard measurement. All of them can be used. We reduce the bandwidth, probably and also the cost. Okay, this will be more reliable. And we can use three-phase model at the substation, for instance, because there are three phases, and each phase has its own measurement. So this increases the redundancy. We can perform topology error, can be dealt with locally, and we can probably detect bad data locally. So this is the advantage of processing here as much information as possible.
It is also to have generalized state estimation because you know the topology
Yeah.
of substation.
Yeah.
You can include.
Yeah. So far, I mean, the generalized estimation promoted by several people, including myself and Brian Stott and some companies, try to deal with topology processing here at the TSO level. With this, it's hard. With this scheme, we could perform generalized state estimation at this level, and then will continue to be batch branch-based state estimation. Good point. Okay, so the idea is, we divide this idea in the Pegase project that we finished 4 years ago. What continues now is the theoretical development we created for this project. So we decompose the multi-level paradigm in a sequence of bi-level estimation. So the 3-level, for instance, we have here 3-level. This 3-level can be decomposed in 2 bi-levels. The first level is the transmission substation and the central TSO. This is the conventional estimator preceded by level 1, which is substation estimation. And then we can move, and what is here, level 2, will be level 1. And each TSO, Spain, France, Portugal, Germany, whatever, will be level 1. This is the conventional estimator, and the results are submitted to somewhere, to a regional place where it is coordinated. Note that this hierarchy is somewhat between fully distributed and fully centralized. Fully centralized means that you should be able to submit everything to here. If you want to estimate the entire continent from Portugal to Turkey, you will need to submit everything to a single point. So this is fully centralized. Totally distributed would be a possibility. Every TSO, will be exchanging information only with their neighbors. And this is an intermediate, somewhat in between. Hierarchically is between fully distributed and fully centralized. Okay. Distribution substation would add another layer. We can have distribution substation. We can perform the feeder. We have published probably paper of all those levels. Feeder distribution substation, then the distribution substation with the distribution system operator, and the distribution system operator can be seen from the transmission system operator as another level. So we can reduce every multi-level environment to a sequence of bi-level problems. So we will focus just on the bi-level problem.
So I keep asking some questions, but does the different voltage levels, like high voltage, medium voltage, you have that kind of structure in the grid? So does that be very natural way?
Yeah, this hierarchy correlates with the voltage, of course. Distribution level is depending on the country. In Spain, for instance, up to 132 and 30 kV is distribution, even though it is not radial, it's mesh. Technically, it should be called subtransmission, but regulatorily, it's called distribution. I mean, it's a mistake, but anyway. So transmission in Europe is 230 and 400 kV. Okay, so and feeder can be medium voltage and low voltage. So this correlates, and this in accordance with the physical and logical structure of the network. Okay. So.
Just to come back to this slide, what is already implemented in terms of exchanges and optimization of communication? So, like for example, on the DSO side, so the level on the left, is that already completely implemented?
Yeah, I mean, distribution systems, the distribution system operator, distribution utilities basically, they have control centers and they have a very similar energy management system to transmission system. For instance, in Spain, both the transmission operator and distribution utility, most of them have a Siemens Siemens system, so state estimation, and so they have similar system. What changed is the redundancy and the kind of information they are using. But yes, they have currently a state estimator here, and they use an external equivalent of the transmission system to perform this state estimator. So distribution companies have a equivalent, small equivalent provided by the transmission, so that they can run their state estimator. So they are doing this. They are doing this. Distribution company is using an equivalent of the transmission system, and some equivalent injection from the low voltage or from the medium voltage. Transmission system are using the border with distribution system. The distribution company are providing them the border information, the border point. And the neighbor, for instance, Spain, communicate with France something to be able to estimate the border. So we already have something like this. We already have DSO is exchanging something with TSO, and TSO is exchanging something with the neighbor, but there is no regional entity yet.
I think there is one in Brussels that's done it after the blackout of 2008.
Yeah, but it's not yet running a state estimator, I think.
Well, it's just maybe coordination.
Yeah, but not real-time state estimation and monitoring every magnitude in real time. This is basically for market congestion, for checking tie line congestion and, deciding whether the market is, the real-time market is, I mean, the day-ahead market is okay. Okay, now some technical details, some mathematics. I like mathematics. I'm here because of mathematics. So now we have, forget about the description, and then let's focus about how we solve mathematically in an optimal manner this bi-level problem. And we are providing a solution which, in my opinion, is the right one. It's optimal, and like other solution, probably Giannaki presented yesterday, this semi-definite problem in relaxation and this kind of thing, which is linearization, something like this. We are providing a procedure which is optimal, provide the right solution, the same solution as if all information was processed at a single point. Okay, so this is mathematics, but this is some application. So the factor solution is an optimal procedure to solve a nonlinear weighted square problem by decomposing or factoring it into two simpler problems. Hopefully simpler problems. It depends if you are successful in getting simpler problems. So this is the original problem, the original nonlinear problem, and this is the original Gauss-Newton normal equation solution. Okay, just for reference, just to compare. So we introduce an auxiliary vector y, which is the size of y is larger than x and smaller than z. So actually, y should be as close as possible to x. I mean, the smaller y, the better. So y is a nonlinear function of x, and z is a nonlinear function of y. So we introduce intermediary vector. So the original nonlinear function is a function of a function. Nonlinear function of a nonlinear function. Okay, it's to be tricky, but we will very quickly understand why we do that. So this is measurement with the errors, and this is a overdetermined system. Hopefully the y is smaller than z, so we can estimate y from this problem. How we estimate y? By running weighted square here, which is this equation. This equation here is the Gauss-Newton, or the normal equation, corresponding to the first problem, nonlinear problem, okay? And then, with the value we obtain here, y, the value we obtain here, we can finally estimate x with the second problem. And the nice thing, and this explains the theory, I have no time here, you can read the IEEE proceeding paper where I developed this as an optimization problem. This can be justified, totally justified mathematically. I will not do that here, just to give you the result. This weighting matrix here, I mean, the accuracy of these estimates I mean, the estimates of the first stage are the pseudo measurement of the second stage. And the covariance of the estimate determine the accuracy of this error, how this is erroneous. If this is very accurate, Y will be also accurate, and this will be small. So the weighting matrix here is the gain matrix here. This one, the gain matrix here. This F1, W, F, this gain matrix here. So the weighting matrix here is the gain matrix here, because the gain matrix is the inverse of the covariance of Y. That's all. There's nothing else. Now we are only dealing with particular cases of this general idea. But this general idea has many potential applications, in my opinion. So now W is diagonal. W is diagonal simply because we are assuming that the errors are non-correlated. But WY is non-diagonal, but sparse, because the gain matrix here is sparse. So it doesn't matter whether this is diagonal or not. What matters is that it is diagonal. Sparse. So no problem. No problem if this is non-diagonal. You just compute this, and you have a sparse matrix here, and you can perform the Cholesky factorization of this matrix. No problem. Okay. Yeah. Yeah, you are right. You are right. Yeah, good point. Good point. Yeah, there are many solutions here. Not so much. This is a problem with the log flow. In the state estimation, this is a least square. Is essentially rather convex. Yeah, you are right. There may be alternative solutions, but so long as the errors in set are relatively small, let's say 1%, 2%, 2%, the other solutions are very far away. So you are probably reaching, if you reach something, if you converge, and you are successful to converge, you reach a solution which makes sense, which is the physical solution very close to the real estate. So this problem of multiplicity of solution is, in general, mathematically speaking, in general nonlinear cases. For instance, in the low flow problem, it's very clear because you have the nose curve and you have the two solutions very close. No, you have in the low flow problem. You have the P and B, and you have this nose curve. And for every P, you have two solutions. This is the physically, real solution, and this is a mathematically spurious solution. And you can, of course, if you start with flat star 1, you convert to this. But if you start with a point here, you may convert to this. So, yes, you are right. There can be multiple solutions, but in the state estimation, it's very unlikely. In fact, I never found in the state estimation an alternative solution, except is there a topology error. If there are no topology error, it's very unlikely that you reach a spurious solution. Yeah, but the geotesting network with the redundancy is very, very, very low, close to 1. And radial. This radiality is more tricky because you can find good solution for the first 3 sections and the bad solution for the last section. So particularly if you use current. If you use current magnitudes, I or I square, then multiplicity of solution is a real concern. There's an entire book chapter in my book devoted to, I wrote personally this chapter because I started my career with dealing with this multiplicity of solution issue. You're right. So I have forgotten about this. But if you measure P, Q, and B, it's very unlikely that you, and you have enough redundancy, it is very unlikely that you face a strange solution. Very unlikely. Good question. Okay. I'm happy that you make question. Please, Carlos.
One more. As for the principle of calculating those Z, Y, and X vectors, they correspond all exactly.
Yeah, this is what I'm going to show you later. I'll try to do that now. So, yeah, good question. So set is the measurement set. X is, it depends. If we are dealing with the international system in Europe, yeah, should be if we are dealing with the estimation of the whole continent, from Portugal to Greece, Z should be all set of measurement, everything. And X should be the state vector of the interconnected continental system, which is 10,000 buses or whatever in the transmission system. So, yes, but we will see this now, right now. Because this is a general idea. It has at least 4 or 5 different applications. And I will begin with the application of multi-area estimation.
Maybe you're going to explain this, but can you correlate from this slide, top-down approach? Start from the higher layer, and then you go down, and not vice versa, not bottom-up.
No, both. Now, we'll see, both. We have to coordinate, we have to exchange information in both directions. But depending on the application. So far, I have not said anything about why. So, okay, this is general. And now there are particular cases which are very interesting and useful in practice. One particular case is when we are able to select Y so that the first problem is linear. This is the case. So if we succeed in finding a Y making the first problem linear, this is very useful. This is basically what is relaxation approximation, what are these kind of things. So we increase the size of X, we replace X by Y so that the first problem is linear. So the first problem provides a suboptimal solution, but solving the second problem gives you the correct optimal solution. So this is linear, non-incremental. Non-incremental is not incremental. Incremental is when it is non-linear. This is non-incremental. Given Z, we obtain Y tilde. And Y tilde cannot be to be recomputed. Y tilde is used here as a pseudo measurement to obtain X, and this is iterative. But this is non-iterative. What does it mean? This means that the first stage is rank only 1. Most important, we don't need to worry about initialization. We don't need to use flat star or the initial values because this is linear. There is no incremental model here. There is no need to choose initial Y. It's linear. We obtain Y directly. We don't need initial values for Y. And of course, there is no risk of divergence. There is no risk of multiplicity of solution. We obtain a Y from this model, which is very good, by the way, if Z is very accurate. In fact, if this is 0, I mean, if Z is sufficiently accurate, very, very accurate, this will be also very accurate. And this will require a single iteration. So the number of iterations of the second stage will be determined by the accuracy of Y, basically. If Y very accurate, a single iteration here would suffice. I will show you some result later. No, I'm happy. If I don't finish on time, we will discuss and negotiate. Reach a consensus about the coffee. We can bring the coffee here. We can bring the coffee here. No, I will tell you what is Y. Y is depending on your problem. If you are trying to perform geographical decomposition, Y is selected in a given manner. If you are trying to solve another, to take advantage of another thing, Y will be different. I will show. There are several ways. Actually, well, the other particular case is when Y is chosen in such a way that the second stage is linear rather than the first one. And this is useful also to give you in advance. For instance, well, I will say, no, not now. I will tell later. It's not a subsequent slide, not now. So different applications arise for this particular case, for each particular case. And the key point is how to choose Y. This is the key point. So far, I have not said anything about Y. So be expectant. I will begin now with 2 important particular applications we have intensively worked on and published. But I want to give you that there are 2 particular cases, 2 interesting particular cases, apart from the general one where both are nonlinear. But when both are nonlinear, probably you don't get any advantage of the factorization. So it's nice if one of the subproblems is linear. So nonlinear, linear, nonlinear, nonlinear, linear. So let's now begin with the first application. The first application is what Carlos was asking me about the multi-area state estimation. I mean, the two-level, we have seen earlier that the multi-level problem can be reduced to two levels. Whether one level can be the substation or the TSO or whatever, or the feeders. And the second level is the one which coordinates the first level. So this is geographical decomposition. So the first objective when selecting Y is to perform straightforward geographical decomposition in order to cope with this spoon of information in smart grid we have been talking about. So we have substation. The substation may be linear. Why the state estimator at the substation is non-linear? Because you have power transformers with non-zero impedances. If you remove transformers, I mean, if you consider transformers as lines, external lines, and divide any substation by voltage level, a real substation is divided in several pieces. This circuit breaker model, there are no losses. So the Kirchhoff laws apply to powers, to P and Q, rather than currents and voltages. So there is a linear model, substation linear model, if a real substation is considered as the connection by external device, which are the transformers. Do you understand, or do you need a figure, a diagram? Actually, I have an hour presentation about this, about this, but not here. I mean, I cannot do that here, I don't have time. So the substation can be linear. We can perform linear substate estimation, generalized substate estimation, including topological constraint, equality constraint, many things, everything.
So if we begin with the distributed substation and you have actual good measurements, and you can get a linear approach with your method, then you can move to the next steps and everything's going to be solved really easily because you have exact or very good estimation. Yeah. So what I may have my laptop here with a presentation devoted specifically to this, and I have a very nice figure that I remove here because I don't have time, where you can show this an example with this substation. So yeah, you are right. You can. Okay, I will see later. Linear. The TSO is the conventional state estimator, which is non-linear. Then the regional multi-TSO can be linear again, because it's just coordinating the estimates of the non-linear. So this can be linear, non-linear, linear. So if we begin with the first problem, we have the particular case linear, non-linear. The first problem. The second problem is non-linear, linear. So both particular cases find application here, in this case. If we are clever enough to, from the very beginning, reformulate the problem of the substation as a linear one, and reformulate the problem of the multi-TSO as a linear one. In case distribution system, there is another level, which is the feeder system, and the feeder system is non-linear again. So the feeder is non-linear because there are impedances. The substation is linear because there are no impedances. The transformers are considered as external lines. The TSO deals with external lines and the estimation of the substation. And the multi-TSO deals with the estimation of the estimates of the TSOs. And it's linear, because all measurements have been used before. So basically, this is the idea. And I don't have so much time now to go into the detail. Well, for instance, for instance, this TSO, multi-TSO, just to take an example. The same could be if this is the substation and this is the TSO, except that we're linear and non-linear. But for instance, in this case, we have a multi-area system. This can be Portugal, Spain, France, Italy, whatever. And we have a Z is composed of the set for each country. Country 1, country 2, country J. Each is a function of the state vector. And in the state vector, we distinguish internal variables and border variables. Border variables are the variables of the terminal nodes of tie lines. So the tie lines that connect every country, the terminal nodes are border variables, and they are shared by all areas. So this is a coupled system. So only border variables couple this equation system. If there were no border variables, it would be a decoupled system. This is the initial situation. This is the conventional estimation. So why do we need a central estimator? Because all those equations are coupled. The border variables couple all equations. So this is a single equation system, coupled by border variables. Okay?
So we can choose y very easily by taking x, the internal variables, and duplicating or replicating border variables. So we replicate border variables. So y is all internal variables plus border variables, which are replicated. So y is larger than x because it duplicates border variable. But the advantage is that now this becomes a fully decoupled problem. If we have duplicated, instead of xb here, we are duplicating the border variable twice in this case. If it belonging to 3 area, it will be triplicated. So we replicate border variable so that we have fully decoupled subsystem, and this is the estimator of each area. Okay? So this is an example of how to choose, answering to Carlos, that how to choose y, for instance, to be able to solve level 1 subproblems individually in a decoupled manner. So we introduce border variable. There is another difference. X refers to a single global phase angle, and y necessarily refers to their local phase angle references. It's a difference. It applies to state estimation. In general, this is not a problem, but we are dealing with phase angles in polar form. So this is a problem. So now each area can solve its state estimation perfectly, no problem. And we obtain the estimate, internal and border, and the covariance, the gain matrix. It is important to retain the gain matrix because the gain matrix will be the weighting matrix of the second level. Remember the factorized scheme? The gain matrix of the lower level is the weighting matrix of the second level, of the upper level. But each area is solved independently. So we can do that with all areas. All areas, we individually, we solve this in a decoupled manner, and we obtain all estimates, area 1, area j, and this is the gain matrix of the internal and border variables, which is the inverse of the covariance of local estimates. But so, what's the problem? Is this final solution? Is this optimal? No. This is what we currently have in Europe. Every area has its own estimator. But the border variable estimated from Spain are not exactly the same as the border variable estimated from France. Plus, France has its own phase angle, and Spain has its own phase angle. So this should be solved in the second stage, in the upper level, in the second level. We must coordinate. The second level, the purpose of the second level is to reconcile the estimates provided by the first level, by the lower nonlinear level. And this model is linear. You can see here the equation is simple. It's basically the definition of y. And y is basically x except for the border and except for the phase angle references. I don't have time to go into the detail, but believe me, this is a linear model. Why is a linear model? Because all raw measurements have been already used at the TSO level, at the lower level. So this is a linear model. Linking y, which refer to local phase angles, with x, which refer to a single global phase reference.
The difference in angles is given from the x.
Yeah, x refers to theta. Theta refers to a single angle. And delta refers each area to its own reference. There's a reference. So basically, when we previously solved for y, we were assuming a reference for each area. And now we have to compute the reference. So this reference is added to the unknown here. So that's the difference. I don't have time to go into the detail, but this equation is linear. Vale? By the way, there is a typo in one of the paper because I forgot this thing. Anyway, there is an interesting thing here. This is 0 if we use local phase references as selected in border buses. Otherwise, not 0. Anyway. Now, this is reorder, and this is the linear problem. This is the second linear problem. This one is solved in the wet tilted square sense because we know the covariance of y. So we solve this. And the covariance of y is the gain matrix. And the gain matrix is composed of blocks. And the blocks can be reordered by internal and border, and decoupling between internal and border. So this is a very sparse block diagonal matrix, already computed available. So we have these 4 major blocks. Each block itself is composed of several as many blocks as areas. And this, the way we propose to perform the computations in as much as distributed as possible. But I will skip this one because there's a lot of algebraic development behind, and I don't have time. So I will skip this one. This is how to solve this, interchanging the lowest information as possible, as low information as possible. Okay, another application which I find also very interesting. Another way of selecting Y. There is no intention here of performing geographical decomposition. Just we can, another example of how to choose Y is to decompose the nonlinear problem. It doesn't matter, I'm not talking now about geographical or whatever. No, I'm just talking about a state estimation, whatever. So decomposing any state estimator into a two-step sequence of simple problems. One of them linear. So this is called the bilinear. Bilinear, or it's not the right name, it's, I don't know how to call it. Anyway, we decompose the problem into a linear one and nonlinear explicit transform, which is trivial, which is one-to-one mapping, and a linear state estimation. So what we are doing is the nonlinear stage. So we are starting with the linear one and the nonlinear. And what we are doing is the nonlinear is further unfolded into a nonlinear transform, trivial transform, and a linear estimator. So we have linear estimator, trivial nonlinear transform with trivial inverse, and linear state estimator. So I'm not talking now. So how can we choose Y to achieve this? So we must now focus and carefully look at the equation. And this is what the other colleagues developed this realization, this semi-definite program, this kind of thing. But we are now providing an optimal solution, not suboptimal, and almost non-iterative. So the idea is to choose the Y as voltage magnitude to the square, voltage magnitude. For each bus, voltage magnitude to the square is U, and for each branch, two variables, VA, VJ cos, VI, VA, VJ sine. This is a very old approach. In the 90s, I published a paper with Esther Romero, my former PhD student, now a colleague, and we were the first to propose this variable for radial low flow. Many people don't know that. Many people, Rabia Jabbar from Lebanon gives credit to our work, but many other people ignore that we were the first to propose this set of variables 20 years ago. But now we are using in non-radial, I mean in any arbitrary system, not necessarily radial. So this is it's clearly the power flow equations are linear because this is UKL, the injections are the sum of power flows. So this is, and U square is U. So this is linear. This is linear. So from the linear model, we can obtain Y estimated, and the covariance of Y, which is the inverse of that, is the gain matrix. Okay? So advantages, I told them earlier, we don't need to choose initial values. This always provides a solution, no risk of divergence, always provides a solution, no problem. And if you have performed the Cholesky factorization on G, the Cholesky is available, and next time you run the state estimator, if only the measurement values have changed, but not the structure, I mean the same measurement set, you don't need to recompute B, because B is constant. So B doesn't change, only changes when you change the set of measurement, not the values. So what we call Wormstern is very quick. This step is very quick, because this is available. I mean, this is available, and the Cholesky factorization is available. So you have very quick. The first step is extremely fast for repeated solution. Then we have the nonlinear transform. The nonlinear transform is alpha. Alpha is the log of the voltages, of the square voltages. Alpha ij, which is a log of k squared plus L squared, and theta ij, which is the arctan of L divided by over k. So these are the three variables. So one variable per bus and two variables per branch. One variable per bus, two variables per branch. So the model is larger. Y is larger than X. That's why this is linear. And the Jacobian here is trivial. The Jacobian is diagonal and block diagonal. So the Jacobian here is one scalar for each bus So 1 for u, 1 scalar, this. I mean, the inverse of the Jacobian, I mean. And 2 by 2 for each branch. I mean, 2 by 2, 2 by 2 for each branch, 1 by 1. So the Jacobian is trivial. Trivial. And the Jacobian is not singular unless the voltages are as 0. So the third step is another linear least squares where the gain matrix is W. W is the computation of the original gain matrix times the Jacobian and the inverse. Okay? So I forgot here tilde. You have the paper. This is a tilde missing here. This is the same matrix. Tilde is missing here. Sorry for that. So this is another weighted least squares problem where the weighting coefficient is inherited from previous steps. Okay? Well, it seems that this is non-iterative. No, it is iterative. Why it is iterative? Because the weighting matrix we are computing here, the weighting matrix at this late step is a function of u. I mean, it's computed for a linearization of f around u, tilde. When we obtain x, we again compute u. We have x, we compute new u cx. If the u new is very similar to the original u, then we have finished. But the u new is quite different from u, then we have to compute the new Jacobian, the new weighting matrix, and then repeat this procedure until the two consecutive values of u are very similar. But how many iterations typically do we have here? Depends on the accuracy of set. If the measurements are typical 1% error, 2% errors, a single iteration here is usually sufficient. Single iteration. I will show you some result now. You understand? I'm now running a little bit faster because I'm running short of time. But
so the first thing to do for this method is to try to find bad data errors and try to cut them out so they don't.
Well, you don't need to do that. You can perform bad data analysis at the end, like in a regular estimator. But you have the choice now to perform bad data here at the beginning. Once you compute y, you can try to perform bad data analysis here. According to our experience, some bad data which are close, the normalized residual are close to 3, may not appear here, but they will appear at the end. But those which are really bad data, which are normalized residual higher than 4 or 5, we also show here are larger than 3. So most bad data can be, in practice, be removed and detected here. And there is no risk of divergence.
Can you try to normalize the data in the beginning and see which values seem to be really far away? Or
no, it is not possible. I don't think so, particularly when there is low redundancy. No, I don't think so. I mean, it's risky. It's risky. This is heuristic. Heuristic here, you must resort to statistics rather than heuristic. So I wouldn't, I mean, there is a prefiltering stage when there are a lot of redundancy. In transmission substation, there is a prefiltering stage. They try to check whether the power flows of the two terminals shouldn't be very different because the losses are small, 2%. So they can detect or prefilter bad data, or a voltage cannot be negative, for instance. So there are some rough, I mean, very basic preliminary checking. But apart from that, you shouldn't remove any measurement unless it's clear for you that it's bad.
Okay, one big question on that. What if you're missing some data? Can this method work with pseudo data?
With what? With?
If you're missing some measurements, some data.
It depends. So long as y is observable, no problem. But even if y is not observable, it can be partly observable. And we have in the paper developed the theory for, in this case. So we could apply this partially to an area, not to the other area. Okay, so let's show some simulation. The average of 1,000 simulation for these benchmark cases, very large cases, 300 bus system. And we obtain the probability density function of the error for 1,000 Monte Carlo simulation. We represent the error in voltages and the error in phase angles. And we perform a single run. I mean, we don't repeat this procedure. We are running this only once. So this, and we don't repeat. So we see here in gray line the conventional Gauss-Newton, single stage. The conventional single stage solution, this is the PDF of the error for this covariance in 4 iterations. And then the factor, single run, is basically on top of the other. So there's basically no practical difference between one and the other. If the error is much larger, then there will be minor differences that will be solved by repeating the last stage one more probably.
From curiosity, are realizations over noise or over different states of the system also 1,000 realizations, Monte Carlo?
Yeah. So no, we are making Monte Carlo with noise, of course. It's different noise. I mean, this we obtain different errors based on this accuracy, of course.
Okay, but
So the set measurement is generated every time.
one state, 1,000 different errors. Okay.
So we generate, from a sat low flow solution, we generate 1,000 different measurement sets. And this is the PDF. And this gives you the filtering capability, no?
What is the runtime?
Sorry?
What is the usual computation of that?
On a laptop, this is a i3, I thought it was an i3 laptop. This is the Gauss-Newton, and this is the one, factor single run. Of course, single run, this is 4 iterations, so this is much faster because in a single iteration, okay? But for the 3,000 bars, even the Gauss-Newton takes 6 seconds, and this approach less than 2 seconds for 3,000 bars.
In real life, what time constraints exist for a result from the estimator?
What do you mean?
How much fast has to be?
It depends on the size of the network. Usually the computers in the control center are much more powerful. They are working station more powerful than laptop. So they can compute this in, let's say, half a second. So this is probably enough in practice.
And how often do you update the state estimation?
It depends also on the voltage level. A transmission system, typically 4 seconds, 10 seconds, depending on the country, on the system. And distribution system, there are no estimators, so who knows? Okay, I will skip this one. So the first linear step always gives an estimate, which is an advantage. We can perform early bad data detection or topology error in this linear step, because this linear step always converges, always provides a solution, and the solution is very accurate. It's set, not very bad. Okay, so I have 10 minutes, at least 10 minutes, because I started at 9:15, right, Carlos? I can stay still 10 minutes, 10, 15 minutes for the last point. Okay, so this idea can be applied in general to almost all nonlinear equation systems. Actually, I recently published a paper in the Proceeding of the Royal Society that you may know, presenting the generalization of this idea to any kind of nonlinear problem. And I will summarize the application of this idea just to the low flow problem, which is because it has in common with the weighted least square estimation the same set of variables, of course. So that's why I'm resorting to this simple problem. I mean, low flow problems share the same y vector as state estimation. So the idea is, we have a nonlinear system, and the nonlinear system typically is composed of the sum of nonlinear terms, of course. In power flow analysis, each nonlinear term is the sum of all branches power flow, which are in turn nonlinear function of the state variable. Okay, so we have, let's say, n larger than n distinct nonlinear term. I say distinct because, for instance, in power flow analysis, the power flow and the other power flow share many terms. You can see it, we saw in the state estimation here, k appeared twice, this nonlinear term appears twice, I mean, the number of distinct nonlinear terms is not very large. So the idea is to introduce y in such a way that the initial nonlinear problem is factorized in this linear stage, nonlinear transform, and linear stage. The main difference with respect to the estimator is that in the estimator, those were measurements, and this was overdetermined. Here, no. These are constraint, bus constraint, power P and Q constraints, and this is underdetermined because y is larger than x, whereas P is size n, and y is size m, larger than n. So this is underdetermined. This is the main difference. Except for that, it's the same as the state estimation. So we are reducing a nonlinear system to first underdetermined system, trivial nonlinear transform with trivial Jacobian and trivial Jacobian inverse to a linear overdetermined system which can be reduced to a least squares problem. So this is the problem. Has this any advantage? Yes, we have tested many practical cases, not only power system, but other kind of nonlinear equation, and it has certain advantages that I don't have time to explain so much. But let's review the procedure. The justification for this procedure is totally explained in the appendices of the paper, so I will not. This can be justified by formulating the problem as an optimization problem, posing the Lagrangian, obtaining the first order optimality condition, and then solving the resulting system. So the justification, I mean, believe me, this is true. It provides the exact solution, the optimal solution, I mean, the only solution. Well, there are maybe many solutions. So this provides one of the solutions depending on the initial point. Here you have to choose initial point. Why? Because the system is underdetermined. So even if it is linear, you have to make a choice where to start from. So we initialize X and solve the first linear problem. The first linear problem, these two steps can be shown to be equivalent to solving a least distant problem. In short, we are obtaining Y tilde, which is as close as possible to YK, but satisfying this constraint. I mean, the P minus this constraint. So the Y obtained in this manner makes 0 this term, and at the same time is as close as possible to YK. This is a least distant problem. And the Cholesky factor of this matrix had not to be updated. It computed only one. So this step is very quickly. Second step, the trivial one-to-one transform. The trivial one-to-one transform, the latest step is a least square problem in which this non-incremental problem, we obtain new X with the Jacobian. Note that the Jacobian here is tilde. The Jacobian is computed for U tilde and Y tilde, not for YK, like the Newton-Raphson. Newton-Raphson compute the Jacobian H for YK. We compute the Jacobian for the improved Y. So step 1 provides an improved value to obtain better X. And then we compute the residual. If the residual is very small, we stop. Otherwise, please note that this residual will be also used in the next iteration. So in the next iteration, the Cholesky factor will be available, and this will be available from the convergence checking. So this is very quickly indeed. This is only forward-backward substitution, very, very fast. So what are the Y? The variable Y are the same, exactly the same we have just been seeing in the state estimation. In the power flow problem, in other problem, think about. So this is the linear equation, the power injection and the voltage magnitude. These are the linear equations. This is the Jacobian elements and the inverse. The inverse is trivial. The inverse is what I have been, this is figure, this is actually one. So each bus has a diagonal and each branch has 2 by 2 block diagonal, which are trivial. You see, the Jacobian elements are trivial. They are available from the computation. These are the results of the computation of the first step. So there is no computation in computing the Jacobian, so to say, except for dividing by 2. Okay, because this value K, L, U are available from the previous step. So the Jacobian is trivial and has trivial inverse. And it's only singular if and only if any U is 0. So long as all U's are non-zero, this Jacobian is non-singular. This is an example for the 300 system. This is the convergence of the factor, and this is the convergence of the Newton-Raphson, starting both from flat start. Seems to be similar, just one single iteration. But, for instance, after 3 iterations, this is logarithmic scale. The Newton-Raphson residual is 10 to the minus 2, whereas the factor residual is 10 to the minus 3, 3 or 4 orders of magnitude. So logarithmic scale sometimes hides the real convergence rate, right? Another test. The 100 bus system, if you convert all PV buses to PQ buses, it is very tricky to solve. The 180 bus system, when you convert all PV buses to PQ buses, the Newton-Raphson performs like this, oscillates, doesn't convert. And the factor procedure converts quickly in 3 or 4 iterations. Okay? There are 2 versions. I don't have time to explain. There are 2 versions, but anyway, you can find in the paper. Another advantage, Another advantage, major advantage. Newton-Raphson works with real arithmetic. Start with real numbers and converges provided there are real solution. What happened? Ayun ahí. I'm finishing. Voltage against P. What happens if we increase P? P and Q. If we increase P and Q, we reach what the mathematician called bifurcation point. The two real solutions merge here in a single double pole, a real pole, double solution. The two real solutions merge in a single solution. When P is larger, we say that the maximum loadability has been exceeded and there is no physical solution, only mathematical solution. And the solutions here are complex, a complex conjugate solution. So two real solutions, a single double solution at the bifurcation point. By the way, the Jacobian becomes singular here. And then afterward, for larger P's, there is a voltage collapse and there is no physical solution. Okay, the factor method converges to the complex solution. We increase lambda. Lambda is a scalar multiplying P and Q. P load, Q load, and P generation. So lambda is a factor. Lambda igual a 1. Lambda igual a 1, sorry. So lambda equal to 1 is base case. And lambda, increasing lambda, 2 is twice the load, 4 is 4 times the load. And for this 14-bus system, when lambda is around 4, you reach the bifurcation point. The Newton-Raphson doesn't work on the right. And the factor procedure provides complex solution. You can see here, the imaginary component is null for real solution, and afterwards the nose curve limit, this is the nose curve limit, this one. So this is the upper part. This is the upper part of this curve, because this is unstable. And when you reach here, afterwards, Newton-Raphson oscillates, doesn't converge. And this solution provides imaginary component. This is the real component and the imaginary component of the vast voltage magnitude, which is a nice feature. And there are also new features we are now investigating. Some many references that you can find all the details I have been providing here. Thank you. 12. So I have given you 5 minutes.
Thank you very